Hello, everyone. Welcome. I just want to say I missed all you guys, and you get to see me virtually now. Mrs. Langle is the other teacher that teaches the same class, and between her and I, we're going to alternate videos each week. So look for her next week, and if you're one of her students, you'll see her next week, and you get me this week. Aren't you guys all lucky? So we're going to get into the wonderful world of parent graphs. And if you had me, we did introduce this before we left, but we're going to just go over these notes right now. Alrighty, so you have the option of copying a blank parent graph toolkit, or you can just look off of the one that is completed, but please go over this as we're going through it. So the very first parent graph that we started with was linears, and that is a line, so that was y equals x. It's the simplest form. We've often seen it as y equals mx plus b. That's the most common form we've seen a line as. But we can also put the a, h, and k in there. And remember, the a always goes in the very front, so that would be the equation y equals a. And then the x minus h are always together. So after that, we had our x minus h, and then we have our plus k, always at the end, that only k. In this case, the a would be our slope, and our h would be any point. Hk is any point on the line. Okay, just remember, a line, it's a straight line. Whether you're m or your a, slope is always rise over run, or the delta y over delta x, which again means change in y over change in x. If we were going to make a table, here's our table. If I plug -2 in, -2 would come out, because again, x always has to equal y. So notice on this table, the x and the y are always equal to each other. And when we go ahead and plot this, we see that it is a straight line. All right, our domain and range, don't forget about that. Our domain would be going left till negative infinity and right to positive infinity. So negative infinity is less than x, which is less than infinity. You can also use this fancy R, x equals, that fancy R means all real numbers, just means every single number going from negative infinity to positive infinity. The same thing with our range. It goes down forever and it goes up forever. So negative infinity is less than y is less than infinity. Or we could also say the y equals all real numbers, whichever you choose to write. And then all these graphs will have a special point. In this case, the hk is any point on the line. All right, so that's our line. The next parent graph we then talked about was parabola. And that was y equals x squared was the parent equation. And again, to create our graphing or general equation, we can always put an a in the very front, so it'd be y equals a. The x and the h are always together, it's always x minus h. And then whatever is being done to the x must now be done to the x minus h. So it's parenthesis x minus h quantity squared, and our plus k still out there, lonely guy by himself. Maybe he'll get a friend one day, but right now he's self-isolating, which is a good thing because that's what we should all do, social distancing himself. Alrighty, the properties is that it's a U shape, because if we look at our table, again, these are my x values. I'm always going to use x values of -2 to 2, except for a couple circumstances, which I'll go over, but from otherwise, -2 to 2 in my x's, and when I plug these x values in, I get 4, 1, 0, 1, and 4, because -2 squared is 4, -1 squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. And when I go ahead and graph that, I do get a U shape. If we're looking at that domain and range, the domain, it goes left forever and right forever. So negative infinity is less than x, which is less than infinity. And my range now, it only goes down to 0. It touches 0, so 0 is less than or equal to y, which is less than infinity. And it goes up forever, which is how we get this infinity. There is a line of symmetry with every parabola. In this case, it would be the line x equals 0. And then, like I was saying, every single parent graph has a special point at hk. In our parent graph, the HK is always 0, 0. So if we look at 0, 0 here, it is that low point, which is what we call a vertex. Alrighty, going on to the next page. Next one is square root, or we can also call this the radical function. The radical, man, like the surfer dude, radical. All right, that's the equation y equals square root of x. And again, we can make that graphing or general equation by always putting the a in the very front. The x minus h always must be together. So the x was underneath the square root, so the x minus h must be underneath the square root, and that plus k, he's social distancing himself like he should be by himself. All right, if we look at the table, now this table, notice we have different x values. So whenever there is a radical, that is when we're going to use different x values, and we are going to use our perfect squares in this case. So -1, we show you can't take a square root of a negative, so that's going to be an error. 0 is a perfect square, square root of 0 is 0, square root of 1 is 1, 1's a perfect square, 4 is a perfect square, square root of 4 is 2, and the square root of 9 is 3. So those are all, that's going to be our table. And when we go ahead and graph that, this is what we get. Notice it only has an arrow in one direction. It has like this starting point right there. So properties, it only continues in one direction. I like to call this the Harry Styles function, you know, the one direction going on there. Our domain, it starts at 0, it touches 0 and goes on for infinity. So 0 is less than or equal to x, which is less than infinity. And the same thing with our range, it goes down and touches 0 in the y's, and then it goes up to infinity. And then our special HK point in this case, again, in our parent equation, there is no h and k, so our HK is always going to be the starting point. So we always look for that little starting point there to determine which directions it's shifted. All right, on to the next, absolute value. So that's y equals absolute value of x. And we can make our graphing equation by doing y equals a always goes in the very front. The x minus h are always together, and since the x is inside that absolute value, the x minus h is inside the absolute value now, and our plus k is still social distancing himself like he should be. Our table, we don't have a radical here, so we're going back to the -2 to the 2's, and just remember, absolute value makes every number positive. It was negative, it becomes positive. It was positive, it stays positive. And then when we graph those points, we get a V shape. And the way I remember this is absolute value creates a V. Value V, you know, get that double V's there. All right, properties, it's a V shape, and there is a line of symmetry with it as well. If we look at our domain and range, it does go left forever and right forever. So negative infinity is less than x, which is less than infinity. And our range, it goes down and touches 0. So we'd say 0 is less than or equal to y, which is less than infinity. And our special HK point in this case, there is no HK in our parent graph, so that means it's at 0, 0 again, and that is a low point. So by definition, it is a vertex. Continuing right along. Next one is a cubic, which would be y equals x cubed. And again, we can grade our general equation. The a always goes in front, so y equals a. X minus h are always together, and whatever is being done to the x is now being done to the x minus h, so x was being cubed, so x minus h must now be cubed, and our plus k still distancing himself like a good boy and girl should. All right, our table. If we look at our table here, we don't have a radical, so again, we're using our -2 to 2, and we're just cubing, so -2 cubed means -2 times -2 times -2, which is -8. -1 cubed is -1. 0 times 0 times 0 is 0. 1 times 1 times 1 is 1. And 2 to the third, or 2 times itself 3 times, is 8. And when we graph that, we get a graph that looks something like this. And yes, it does slightly go off the graph that we have here, but that's the shape it looks like. The properties, it's like a steep curve. Notice how fast it's growing. It does flatten out right here, which is very important to help us determine how it shifted, and then it grows very fast again. Our domain, it does go left forever and right forever. and it does go up and down forever as well. And then our HK point is again, it's at 0, 0, because there is no H and K in our parent graph. And at 0, 0, notice how it's growing really fast. It flattens out and then grows really fast again. So the HK is where the graph flattens out. So again, that's how you can always determine how the graph is moved. Left, right, up, down. All right, our next one is the cube root, which would be y equals the cube root of x. And again, we can write our general equation. The a always goes in front. The x is being underneath the cube root there, so the x minus h is now underneath the cube root. And our plus k still by himself k, by herself k is what they're calling her these days. Our table, this has a radical, so we are going to be using the perfect cubes here. So -8, -1, 0, 1, and 8, because if I plug -8 in here, this is saying what times itself 3 times is -8, which is -2, so the output's -2. -1, if I plug -1 for x, it's saying what times itself 3 times is -1, which is -1. 0 is 0, because 0 times itself 3 times is 0. 1 is 1, because 1 times itself 3 times is 1. And then if I plug 8 in here, again, this is saying what times itself 3 times is 8, which is 2. So 2 is the output there. And when I graph that, it looks kind of the opposite of what we just had above. This one is now very wide instead of very tall. All right. So some people kind of call this like a vertically compressed S. Think about if you had an S and you push down on it, it kind of looks like what this graph is. The domain and range are still both all real numbers. Are going from -infinity to infinity, because it goes left forever and right forever for our domain, and our range, it does end up going down forever and up forever. And then our HK point in our parent graph, there is no H and K, it's at 0, 0. And so now this is just the opposite of the cubic. Notice how this graph grows very slowly, but at 0, 0 grows actually the fastest, and then it grows really slow again. So the HK for the cubic is the point that grows the fastest. All right, moving right along. Exponential growth is our next graph. That's the name. That is y equals 2 to the x, and we could really put any number greater than 1 in this spot, but for simplicity's sake, we're going to do 2 to the x. This one's a little tricky because the x is in the exponent, so when we go to make our general equation, the a is still in the very front, like it should be. Now that the x is in the exponent, remember the x and the h always have to be together, so the x minus h are now both in the exponent. So the way we do that is we put that x minus h in parentheses in that exponent, and our plus k still out there by himself, socially distancing himself. All righty, now if we look at that table, there's no more radical, so we are doing -2 to +2. Just remember, anything to the 0 power is 1, so 2 to the 0 is 1, 2 to the first is 2, and 2 to the second is 4. Now these negative exponents, just remember a negative exponent moves that base to the bottom, and then the exponent becomes positive. So if I had 2 to the negative first, that would make it 1 over 2 to the positive first, which is just 1/2, and 2 to the negative second, I can put a 1 on the top of that, so it becomes 1 over 2 to the second, which is 1/4. And then there's our graph. There's some special things about this graph. It is growing very fast. You've probably heard the word exponential a lot with this COVID-19, how the spread is exponential, growing very fast, unfortunately. There is also a horizontal asymptote here. Remember that MC hammer line, you can't touch it. Right here, you can never touch 0. It never touches 0, so that's what a horizontal asymptote means. Our domain, it does go left forever and right forever, so -infinity is less than x, which is less than infinity. But our range, it gets really close to 0, but again, since we can never touch it, it does not equal it. So it's 0 is less than y, which is less than infinity. And then our description, in this case, there is no, the h still does move the graph left and right, but remember, if you look at our parent graph, there is no h and k in our parent graph, and there's nothing at 0, 0. So we're looking at just the description of the k, and the k always will tell you where the horizontal asymptote is. So if my k was 3, that means my horizontal asymptote is now at 3. It's never going to touch 3. If my k was -5, my horizontal asymptote would be at -5, and my graph would never touch a y value of -5. All right. The one that relates to exponential growth is exponential decay. And so that's y equals 1/2 to the x. So again, this number, the 1/2, could really be anything between 0 and 1. We're going to keep it at 1/2 for simplicity's sake. And again, the equation would look very similar to above. The a is still going to be in the very front. My x is in the exponent, and the x minus h are always together. So x minus h is now in the exponent. Again, we put that in parentheses to show that it's in the exponent, and our plus k still by him or herself. If we look at our table, we do not have radicals, so we're going back to the -2 to 2. And again, anything to the 0 power is 1. If I plug 1 in, 1 to the 1/2 to the first is just a half. 1/2 to the second, I square the top and bottom, get 1/4. And then the negative exponents, remember, flip that base. So when I have the -1 as my exponent, I flip that base, which becomes 2. And then the exponent's positive. So 2 to the first is 2. And then 1/2 to the -2 for this one. I flip the base to get it a positive. So 1/2 flipped is 2. And then the exponent comes positive. So it'd be 2 to the second or 4. So our graph would end up looking like this. So it's going down very fast now. So this is a decreasing curve with a horizontal asymptote still. Our domain is still -infinity is less than x, which is less than infinity. Goes left forever, it goes right forever. And the range is 0 is less than y, which is less than infinity. Because again, we're never touching that y equals 0. Can't touch it. MC hammer, the asymptote line. And then similar to what we just had above, the h still does move it left and right, but it's not actually a point on your graph. The k, though, again, will tell you where your horizontal asymptote is. And last but not least, we have the hyperbola, which is y equals 1 over x. You may also hear this as called the reciprocal function. All right, so y equals 1 over x is y equals a. A is still in the very front. Now notice where the x is. The x is in the bottom, so your x minus h must now be on the bottom. So it's 1 over x minus h. And our plus k is out there at the very end, still social distancing him or herself. Very good. But the k will always be by itself. Just remember that. Here we do not have a radical, so we are doing the -2 to 2 in our x's again. And when I plug these in, if I plug a -2 on the bottom, I get -1/2. If I plug a -1 on the bottom, I get -1. If I plug 1 on the bottom, I get 1. 2 on the bottom, I get 1/2. Now this 0 error, if I plug 0 on the bottom, remember you can never divide by 0. So that's why we have the error. 1 divided by 0 is an error because you cannot have a 0 on the bottom of your fraction. And when we go and graph this, it would look something like this. And remember, this is the graph that has 2 asymptotes now. The 0 error means the x value can never touch 0. So I drew a vertical horizontal line, or sorry, vertical dotted line here, which is signifies, yeah, that's the word, and asymptote, never touching it, MC hammer. And again, we're also never going to touch 0, a y value of 0, because I could plug any number in here for x. 1 over a million is close to 0, but still not actually 0. So we have 2 asymptotes in this case, a horizontal and a vertical. So that's our property, horizontal and vertical asymptotes in this graph. That makes your domain and range a little tricky because it does go left forever, it goes right forever, but it never touches the one value where the asymptote is. So in this, for our parent, it's -infinity is less than x, which is less than infinity, except x equals 0. And then our range, it goes down forever, not forever. So that's why where we get this -infinity is less than y, which is less than infinity. But there's one y value that never touches, it never touches 0. So we write that exception y, except y equals 0, because it can never touch those. And then our last part here, the HK. This is where the asymptotes intersect is our HK, because if you look in our parent graph, there is no HK, which is again is at 0, 0, making your HK for your parent graph at 0, 0. And if you look at 0, 0, there's no point on our graph, but it is where those two green asymptotes are intersecting. So that's our parent graphs. I hope you enjoyed it. Adios.